All right, let's get started. Good morning. All right. Let's look at the calendar here. So remember, next Monday and Tuesday we have no class, and then Wednesday through Friday is Thanksgiving break. So that's that, right? Someone's happy. All right, so today we're going to look at the first part of 10.3. We'll look at what's called polar coordinates. And it's named polar because they're really, really cold. No, they're not. They're actually pretty cool. Let's stop. Okay? You're going to be seeing a lot of this in the next calculus course when you take it next semester. So just give you a little bit of taste, and then so when you see it next time, you'll be prepared to handle it. In the usual Cartesian coordinates, we specify a point by telling us what the x is and what y is in a 2D. In 2 dimensions. And 3-dimensional is the same thing. So a point in 2D is specified by its x and y location. Right, so we know when we say 1, 2, we're talking about this point right here. When we talk about negative 2, 1, we're talking about this point right here. Okay, so it's a very simple system, and we're very used to it. Now, polar coordinates is a different way of specifying the location of a point. Again, in 2D, and we specify the location of a point by its distance from the origin. And the origin is also called a pole, hence the name polar. And an angle. From the what's called the polar axis. Which corresponds to the x-axis in the Cartesian coordinates. So for instance, in the polar world, if I want to specify the location of a point, I first need to tell you how far it is from the origin. So if I write a point, let's say 2, comma, pi over 3, what that means is I need a point that's at a distance of 2 from the pole and at an angle of pi over 3 from the positive x-axis. So right here. Right? Does that make sense? You tell me how far it is and at what angle it is. It's similar to how we locate things on a map or using the directions, right? So you might, if you're sitting on the ground, you might be looking at an airplane. You'll say it's 2 miles from me and 30 degrees east, north, whatever. Another point that's put on here as another example. Oh, by the way, r can also be negative. So this point here, one way to specify this point is that it is at a distance of -2 with an angle of pi over 3. So I find my angle pi over 3, and instead of going towards away from in that direction to get my positive distance, I actually go the negative distance to find this point. So r can be positive or negative. Make sense? So that's the basics of polar coordinates. Let's talk more about this negative r and the multiple ways we can specify the same point. And really theta. Another consequence of that is that we have no unique way to specify one point. Yeah.
-2 and pi over 3.
Yeah.
How do we know it's any different from -2
And the negative 2.
In the second quadrant?
Oh. Well, in the second quadrant, my angle would be different. Well, actually, if you wait just a second, we're going to be talking about multiple ways of talking about the one point. Maybe that'll answer your question. If not, then we'll come back to it, okay? All right, so again, there's no unique way to specify that one point. In the Cartesian world, when you say 2, 1, there's only one way to talk about it, no other way to talk about it. But let's look at that point I used in my earlier example right here. 2 comma pi over 3. Another way to talk about this same point, what I could also do is I can go negative theta this way. It'll bring me to this dotted line. And then I specify a negative r to go back to here. Right? First, you look at the angle and tell you where you are. So I need to go negative 2 pi over 3 this way, puts me on this dotted line. A positive r will put me in the third quadrant. But I want to go in the first quadrant, so I specify a negative r to go into the first quadrant. Make sense? Okay? Now I want to take 1 minute and find at least 2 more ways to specify that same point. At least 2 more. All right, so who's got 1? One more way to do it. What you got?
Negative 2, 4 pi over 3.
-2 and 4 pi over 3. Okay, 1, 2, 3, 4. Well, I'll write it down and then we'll talk about it. Okay, I'll put a question mark next to it. Who else? That would be 7 pi over 3. You buy that? Okay. So question mark. Anyone else? And -5 pi over 3. All right, so let's look at these things here and then see if we agree with that. What do we think of the first one here? -2, 4 pi over 3. So let's first find out where 4 pi over 3 takes us. Pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. So this puts us in the third quadrant. And to go back into the first quadrant, we use a negative radius. So that looks okay, right? We agree? Yeah. Okay. Do we agree that this looks good? Yeah? Okay, yeah, that's good. 2, 7 pi over 3. Well, that one's pretty easy to figure out. That's just this guy here, and then go one more circle around. That's adding 2 pi to that angle. So 7 pi over 3 is 2 pi plus pi over 3 and a positive radius. So that looks pretty good. And 2 comma 5, -5 pi over 3. So let's see. -1, 2, 3, 4, 5. Right? -5 pi puts us here. And I want to stay in the same quadrant. So a positive r puts us in the right place. So that also looks pretty good. Okay, does that make sense? How you can specify that one point in basically infinite number of ways? Yep? And we don't have that flexibility with Cartesian, right? The point 2, 1 is 2, 1. There's no other way to talk about it. But with polar, because of the way we spin around either way, and the radius can go either way, we have a lot of flexibility. Now let's talk about how we can go from one to another. How do we go from Cartesian to polar and back and forth? First, let's look at going from polar back to Cartesian. So what we do this when I specify a point in the polar coordinates, and you want to find the corresponding Cartesian. So let's put down a random point somewhere, and it's at r comma theta, right? Radius, whatever, how far is it away from the radius, and where it is. Once again, the theta tells you quadrant, and r tells you whether to go into the quadrant or go into the opposite quadrant. Now, if we make a triangle this way, then, of course, the base here is x, right? And this right here, the height is y. And this right here is r. And, of course, theta is sitting right here. So using trigonometry, we can relate r theta to x and y. For example, we know that cosine is adjacent over hypotenuse. So this tells me if I want to know what the x-coordinate is, once I know r and theta, then I need to use this equation. Right? And I can find y exactly the same way by using a sine. Sine is opposite over hypotenuse, so y over r. Therefore, y is equal to r sine theta. Another potentially useful relationship between the two is x squared plus y squared. If you add these two squared together, you get r squared cosine squared plus r squared sine squared. And that gives you just r squared. So that's also a potentially useful information. But these two equations in a box are more directly useful. Okay? So for example, let's try this on something. We have a point that's negative 2 pi over 3 in polar coordinates. Let's find out the corresponding location in the Cartesian coordinates. Now, one thing that really helps is if you can sketch out where the point is, then you can right away know what the sign of x and y should be. And that's an additional way to check if you have this correct. All right, so pi over 3. It's this line right here. This is pi over 3. So obviously that's also pi over 3. And then if r is positive, we'll be in the first quadrant. R is negative, so we're going to the third quadrant. Okay, so what you can do here is to remember what the sign should be and just work with the triangles. Right, so this is going to be our y. We know it's got to be negative. This is our x. That's got to be negative. And the equation will also tell you exactly the same thing. R cosine pi over 3. And what's cosine of pi over 3? One half, good. Minus 2, 1/2 gives me minus 1. And that looks right. At least the sign is right. Yep. We know it's got to be negative, and it is negative. Y, same thing. Negative 2 sine pi over 3. And what's sine of pi over 3? Yep, so this will give me negative root 3. Okay, so in the Cartesian coordinates, this point is negative 1, negative radical 3. Make sense? And there's only one way to specify this point in Cartesian, right? That's exactly what it is. No other way. We have very little flexibility with Cartesian. But polar, we can do just about anything. And one good thing about the polar coordinates is it's very useful for things like circles or things that look like circles. For example, equation of a circle with radius 3 centered at origin is simply r equal to 3. Notice that theta is not specified. And when it's not specified, that means that you want to include all the possible theta you can have. So for example, we start at theta equal to 0, r equal to 3. That gives me this point. Then I want theta a little bit more than 0, so next one, next one, next one, and so on. I keep accumulating the points until I get all the points on the circle. So notice that the equation for a circle is very, very simple in the polar coordinates. And we know that in the Cartesian, it's not terribly difficult, but there's more stuff to write. Right? X squared plus y squared is equal to 9. If you want just a portion of a circle, it's the same idea. So for example, let's say we only want the half of what's in the first quadrant. So I just want one slice of that in the first quadrant. So r equal to 3, that specifies where the shape came from. But I only want just a slice of that. So we say we bound theta. Right? So this will give me just that little arc. Make sense? Okay, now I want you to describe this either by sketching or in words. Take 1 minute and sketch if you can. If not, describe in words what this thing looks like. All right, so what does this look like? Tell me more. Okay. Yeah. Right. Okay, so theta equal to 0 is right here. And this is theta is equal to pi over 2. We want everything in between, everything in the first quadrant here, and starting from r is equal to 1, which is right here, and r is equal to 5. So it's not drawn to scale, but get the idea. So like that, right? It's a portion of a ring, basically. Does that make sense? Now, what if I change the inequality here to strict inequality? By the way, this is strictly greater than. So we actually do not include exactly when theta is equal to 0 and theta equal to pi over 2. Okay, so with that in mind, what would this look like?
Make the lines dotted that are going from 1 to 1 and pi to pi.
Right, so same shape, right? This time we don't want the boundaries. We want everything in between, but we don't want the boundaries. Okay, so that's how we describe various shapes in polar. Now, sometimes you'll be given an equation in polar, and you like to find out what it looks like in Cartesian. Now, one thing is because we can usually sketch things in Cartesian pretty easily, but we're not familiar with polar necessarily. So, for example, if I have this equation, suppose I want to sketch this thing. So one thing that might help is to find out what it looks like in Cartesian, and perhaps it's a shape that we're familiar with, then we can sketch this pretty easily. These two equations we saw earlier will be tremendously useful in accomplishing this conversion. All right? So first of all, let's see if we can simplify this a little bit. I change tangent to sine over cosine, and change secant to 1 over cosine. And let's multiply the cosine square to the left side here. I'll do it this way. Okay? Now, right away we can see that this is x. And I would really love to have an extra r here to make that another x, and then an extra r here to make that a y. So let's multiply one more r to both sides. And that's going to give me the extra r's I want. Right? I can multiply both sides by anything I want, including r. So now I got the missing r's I wanted. Now I can just directly change things back to x and y. This is x. This is x. So this is simply x squared equal to y. Right? Okay, so what shape is this? Parabola. Tell me more about it. Which way does it open? Up? Right? Left? Down? We cover all the bases. Up? The answer is yes. Right. Y is equal to x squared. That's the basic upward opening parabola with the vertex at the origin, right? So now you see an example where certain shapes in Cartesian are very simple, very easy to recognize, but their corresponding form in polar can be quite strange. Okay? All right, so let's look at the other conversion. Last time we looked at how we can go from polar to Cartesian. Now we'll look at a Cartesian to polar conversion. This is a little bit more complicated, and you'll see this in a second why. Okay, so once again, I'm going to specify some random point, x comma y, whatever x, y you want it to be. And I will again build a triangle this way. And x, of course, is the horizontal width, and y is the vertical one, and this right here is our r, right? To find r, so this means going from x comma y to r theta. R is the easiest one to find. We simply use the Pythagorean theorem to do that. All right, so that's easy. X squared plus y squared. What about theta? Yeah, so we look at this thing here. Tangent of theta is the opposite over the adjacent, right? So theta is equal to the inverse tangent of y over x. So these are the equations we can use. Now the complexity comes in play because remember, we can also find a negative r, but then we have to adjust the theta. If I use this equation here, I will always get a positive r. But I can also manually adjust that to a negative r and then change the theta by going halfway around the circle. So for example, let's look at the point in Cartesian. It's 5 radical 3 comma 5. And it's very important that you nail down the quadrant right away, because theta depends on the quadrant. Quadrant first, right? So where are we? We are, we're here. So we're in the first quadrant. Okay, so let's use the formulas we got. First of all, r is equal to x squared plus y squared. So 5 radical 3 squared plus 5 squared under root. And that's 75. That's 25. Radical 100 is 10. Right? And then theta, inverse tangent of y over x. And this requires you to find the inverse tangent of, I got this backwards, didn't I? Yoink. Y is 5. X is 5 radical 3. So this is inverse tangent of 1 over radical 3. Anyone know what that angle is? Sine is 1/2, and cosine is radical 3 over 2. Pi over 6. Yeah, that sounds about right. That sounds exactly right. Okay. Right? So that's one way to talk about this point. We can do pi over 6 and a positive r, 10. Give me another way to specify that same point. How about if I specify I want a negative r? I want it to be negative 10 here. What angle should this be then? Seven pi over 6, right. 7 pi over 6 will put me here, but I want to go back in the first quadrant, so I can do negative 10, 7 pi over 6. Okay? So on WebAssign, the problem will be like this, and it'll specify I want a positive r, I want a theta between something and something, and you need to think about how you need to adjust that point to put yourself in the right quadrant. Okay, now let me show you why it's important to get a quadrant right. So I'm going to use the same numbers but negative this time. So first we notice that this is in quadrant 3, right? And the r part of the equation is very simple. It's still the same thing, radical sum of the squares. There's no ambiguity there. But when you find the theta value, notice because the minus signs cancel, this equation looks just like the previous one. And that's because tangent is positive in 2 quadrants, right? Is that a question? How is what in Cartesian? I scratched out polar. I need to do a better job with that. But I can't do it anymore. It'll go through. It's just Cartesian. Sorry about that. So notice here, we're doing an inverse tangent of the same thing we did earlier. Now, if I didn't check the quadrant and I just went directly to the equation here, I'll find out the theta, pi over 6, right? If I just look at this equation without remembering where my point is, and this would be incorrect. That puts me in the wrong quadrant. And this is called the principal value. To be in quadrant 3. So theta really should be 7 pi over 6, right? The solution I get out of this equation is that, but I have to adjust that so I get in the right quadrant. So what you want to remember here is every time you do an inverse tangent, the principal value could be in either, the angle could be in either quadrant. So when you get a principal value here, you have to make sure you adjust so you land in the right quadrant. And that's called a quadrant check. This is a very serious problem when you use computers to solve this kind of thing. A computer doesn't really know where that point is. That's where the programmer, you, have to come in and say where it should be and then adjust it. Yeah?
Can you keep theta as pi over 6 and
You could, yeah. He brought up a good point. You could keep pi over 6 and then change r to negative. That would be fine. Yeah? But once again, if the requirements say I want a positive r, then you have to check your angle. If there's no restriction on what you can give me back, then you're free to do whatever you want with a negative r and then the same angle. And on WebAssign, they will specify I want a positive r, for example. In that case, a quadrant check is very, very important. Okay? So again, like I said, this is a problem with computers. This is called quadrant ambiguity. When you just solve that equation here, you don't know where you are. You have a possibility of being in 2 different quadrants. All right, let's do one more example. This time, let's translate a familiar equation in Cartesian into polar. Okay, so y equal to x. That's just this line right here. So this is about as simple as it gets for equations in Cartesian. But in polar, these things don't always look very nice. I can change y to r sine theta and x to r cosine theta. And look, obviously the r's cancel, so we have that, right? And now I could also divide by cosine on both sides and get tangent of theta is equal to 1. Or I could say theta is equal to pi over 4. Right? So this is the equation. Either of these two is fine. The equation of that line in polar coordinates. Notice that r is not in the equation. So what this is saying is that locate pi over 4. And since r is not specified, that means we want to accumulate all the points on that line, all the possible r, which if you think about it makes perfect sense. This line is making an angle of pi over 4, right? So that's the equation. Let's do one more. This one's short. Y is equal to 1. Same way we do it. So r sine theta is equal to 1, right? It's divided by sine. And there we go. We get this equation. Now, when you look at this equation, if I just give you the equation without if we hadn't gone through this step and you just see this equation, you probably would not have recognized that as being a straight line, y equal to 1. Okay? So this is one of the major limitations of polar coordinates. Certain equations, like line, for example, are very strange looking in polar. But polar is very good for circles and things that are related to a circle, like ellipse and other things. Okay, that's it for today. Remember, we have no class on Monday, no recitation on Tuesday. So have a good break. And I will see you again the Monday following 2 weeks, basically 2 weeks from now. No. Yeah, you know what I mean. Enjoy your break.
about your gift. She wanted to watch her react. What? Here, you guys can sit up here. You two can sit up here. Plug it in. Oh, it's already suction. Oh, it works. Okay. Okay. Thank you. Oh, okay. Oh, maybe we could just plug 2 in and then I can keep mine on. I'm gonna set up.